sort of, kind of. And so Keith is not going at the moment. This beauty, you would think I've seen it before. Difficult cases. And I'm like, yeah, that's fine. Okay, is correct. 0, 1, and 2 is odd since it's choice. You could argue I'm gonna choice my way along. Why am I recording here? I thought I stopped this recording. Restart recording here. Yeah, okay. It's Coffee Compiler Club, here to talk about anything to do with compilers and language runtimes and type systems and garbage collection and whether Scala is the C++ of Java or not. And we've had a long, interesting conversation about the merits of Scala that are off camera and appear to want to stay that way, which is too bad. They're fun. Being recorded live, be on YouTube within an hour, 2 or 3, fine, whatever. That's into my set.
You know what's interesting though, on the same topic, if you look at C++, when did it really start actually looking like a properly designed language?
I grabbed
it was 15 years ago with the standardization work and what's his name from Microsoft who helped make sense of all the specs.
Sutter?
Oh yes, Herb Sutter. Yeah, Herb Sutter. And it's like the adults finally came into the room and said, okay, let's take this pile of trash and sort it into something beautiful. And I love to hate C++ and I hate to love C++, so it's definitely a love-hate relationship, but it really matured. And if they could only jettison the 90% of the language that sucks, it would be pretty impressive.
Interesting.
I mean, even C++ 11 changed a lot.
Yeah.
Did they ever drop anything?
No, they can't. I mean,
Yeah,
so
well,
it's basically most of the, you read through the discussion threads on the forum.
Yeah.
With the spec group and everything, and they're like, oh well, yeah, don't use that feature and don't use that. So basically, there's like 70% of language is deprecated. You should never use new or delete. You should like just a list of stuff you should never use is enormous.
But Java's in that same place. The main value of Java is that there's a lot of Java code in the world that you can interoperate with.
But the set of things that you're told to stay away from, I claim, is fairly limited. Like stay away from
because the language is actually fairly limited. In fact, basically the only things you're told to stay away from are the stuff that was there before 1.0, so the .98 release, and anything added in Java 5 itself. So anything to do with generics or
I've certainly found in a corporate environment, it's very valuable to have a linter that says, hey, you just used a Java thing that's on the nope list. Don't use java.util.random, use java.cryptography.random. Don't use java.url, use java.uri.
You probably should not use java cryptography.random.
Yeah, I hadn't
That
heard
is
that.
probably a mistake in most use cases, because first of all, it doesn't have a random distribution.
Random or the cryptography random?
Cryptographic random is not a random distribution. It's a cryptographically secure random. There's a difference between random and random.
Yeah.
What you should be using, Mark, help me out here, is the threadlocal random implementation.
Oh, yeah, threadlocal.
Because it's free.
Really?
Yeah, it's very, very fast. Oh, it's zero cost, basically.
Well, but it also produces a reasonable numbers. Like
Yeah. I mean, all the pseudo-random algorithms these days are very good.
Okay, because the one that Java originally shipped with was not good.
Certainly not for anything.
This is much
specific.
more recent.
Right.
Yeah, because there was a discussion of
Java 1.6
replacing,
recent.
there was a discussion of replacing java.util.random with a better random, but there was too much code out there that relied upon the fact that occasionally java.util.random gives you the exact same number twice in a row.
Really?
So there were things that were like loop until random gives you the same thing twice in a row. And my game
No.
will have this semi-deterministic feeling thing. So they couldn't increase
Wow.
the amount of entropy in java.util.random because it broke old games.
Well,
Oh,
it's
I
easy.
would-
Just always use
No.
threadlocal random.
Okay, fine. Yeah, I just said, people who write that code get broken when they upgrade, and then fine, they get broken when they upgrade. Okay.
Yeah.
Fine. Yeah,
think
H2O, we had to
Java-
have
It's
a-
definitely good to have some lint rules of this is an old language. Please don't use feature X if you're writing new code.
I think Java actually switched to using the same algorithm we picked for the pseudo-random in ecstasy, which is called the Zorshift star algorithm, which is it's brilliantly good and brilliantly cheap. And I
So we
wish I
used
could
one
take credit
for
for it.
H2O that
but
was distributed and deterministic, so we could spray pseudo-random calculations across a cluster and have everyone get the exact same sequence of random numbers. It's all different for every core, but it was entirely repeatable. If you changed the order of calculations or you changed the size of the cluster, whatever, they'd all recompute the same thing. So we had a custom random util that was, you could jump ahead millions of random numbers and then have that guy start there or whatever you had to do. So everyone got a pseudo deterministic but repeatable in a distributed environment. It's a little more obnoxious than your usual random. But then in the end, I think we tried a bunch, and I think we decided we liked pretty good random numbers. Something like pretty good something, PGR something.
Right.
Which appeared to give good answers in terms of randomness. Like we did serious math on our random numbers because we had issues with the original randoms that we were using, and we needed high volume. When we needed randoms, we needed super high volume randoms, so they had to be super cheap. So all like the mersenne twisters and shit were too expensive, and we ended up with this PGR thing. I could probably drag a link. Oh, and I have.
Question out of curiosity, was mersenne twister ever good for any use case at all under any circumstances? I cannot think of any actually.
Well,
I'm serious.
We used it as a high quality random number when you wanted 1 or 2, but when you wanted 1 billion, it was just too expensive.
Yeah, and I remember that even at the time of mersenne twister, there were already better algorithms that were also less expensive.
Although cameras have gotten so cheap now, it's pretty easy to get random numbers by just sticking a camera on a motherboard in a data center.
Yeah, I'm sure that's not a security problem.
I was a little bit
How did-
surprised when I found
how
out you
did
could
they
get
defeat
high
my
quality
air
random
gap?
by pointing a camera at a wall of lava lamps. I was more surprised when I realized you could get high quality random by pointing a camera at the back of the camera lens. Just keep the shutter closed, film the blackness. You get a bunch of
Yeah.
randomness in the low bits, hash the thing, high quality random, as much as you could care for. The back of the lens cap is about as random as the wall of lava lamps was.
And still better than mersenne twister.
The secure random stuff in Linux, I think, tries to sample the environment.
Yeah.
So like you need sources of random, like typing, mouse movement, network packets.
Right.
And so when things are quiet, it takes longer to get a random number
Yes.
out.
I remember hearing that.
Uses up its pool.
Right. You could drain its recording of random bits out, and then
Yeah,
it would be waiting
it
for
has-
network packets of shit to come by.
It's what they call a source of entropy. So it accumulates entropy, and then if you ask for random numbers fast enough, you actually deplete the entropy. But Intel also now has an instruction that's pretty close to true random. I can't remember what it is, but I think it uses like heat sensing or something as part of its input. So it's you know, it is actual entropy measurement.
Oh, I always assumed it was using reverse breakdown of a diode to get that random.
Yeah, I thought it was right. I'd heard this going around. Okay.
Yeah,
Right.
I'm not I'm not
Yeah.
that understanding of electronics to even know what you just said, Aaron.
Yeah, I was once a double E before I got all software-y.
Yeah, me too. But I don't remember that particular one, but I knew that you get all kind of randomness by hanging open ends off of sensors and just have them floating in the air.
So I had a separate question I wanted to ask this group that I'm not sure if it's a language question or a syntax question or a VM question, but more and more we're seeing projects that want to have some kind of gas fees. You can run this thing for a small amount of time or a small amount of memory or various kind of resource limits.
Yeah.
What features do you want in the VM versus in the language to enable sort of efficient structures for, hey, I would like you to run this eval or this lambda, but here are all of the limits, but I don't want to spend all of my CPU just accounting for the fact that I'm trying to limit CPU.
Yeah, it's a denial of service prevention.
You have to ask too about what's important. And generally speaking, when you're counting clock cycles, you don't want to do it transactionally. And this is the same thing for like counting web page hits and stuff like that. A lot of early developers on the web would, you know, on every web page, they'd read a number from the database, increment it and write it back out and commit the transaction. And they couldn't understand why their site had a big picture of a whale on it. And Twitter.
Yeah.
That's okay. They solved that problem by switching to Scala.
And it turns out that most of the time, you don't care if you lose the counter, right? So you have a machine fail and you lose your last couple seconds worth of page counting. No one really cares. Even in an advertising system where you're getting paid per advertisement, the advertising companies finally realized that the amount that they were spending in terms of both time, which is the more expensive thing, and hardware and whatnot, trying to transactionally tabulate the information was just ridiculous. So, because what happens is if the slower an ad system responds to a query for an ad, the less likely the ad gets shown at all, because the ad aggregation networks basically give you a certain number of milliseconds and then just ignore you. So the
So what's going on here is there is a real-time system, the ad aggregation, who then has to do not necessarily denial of service per se, but he has to maintain real-time behavior because the end users are like, 2 seconds, you're too slow, I'm moving on to Amazon, and you know, and you lost your sale.
Not to include, there is a bidding who
Right.
gets to show on the ad.
that's correct.
I'm not even going there. I'm just saying, real world
So
is real.
basically, when you're doing the accounting for it, you don't want to actually write the data out. You just want to hold it in memory and then every second or whatever, flush it. And so if your machine dies and you lose a second of data, it's possible you lost 3 cents, right? But, you know, is it worth losing the $1 million to keep the 3 cents? It's kind of this, you know, that's the trade-off, which is very reminiscent of the garbage collection and that missile where they calculated the amount of memory it would use for a transcontinental flight, put that much memory in and got rid of the garbage collection. It's a nuclear missile, you know.
And then it collects.
Then it collects.
Yeah, kinetic garbage collection has its limitations.
I've long wanted to see some sort of support for, I want to say, hard real times and resource allocation put into a language. And you know, I got sidetracked in the AA just doing type theory things, which I claim is still looks like I'm running to completion here. But yeah, I'd love to see a serious look at, you know, here's some pile of code. I want to put some kind of a number or constraint on it that says it'll run this fast, or the compiler will tell me. And maybe, you know, as part of the compilation linking step, it includes the backend that I'm targeting, because if I target a, you know, Raspberry Pi versus my x86 desktop, I have more or less cycles per, you know, per second time. I get more or less compute done. There's a bunch of random things to be thought about that have not been thought about. Like if you go back to IBM, and their mainframes, when they first came around, they did a lot of job scheduling shit because they were used to talking with people who were working in real world where job scheduling meant I moved the truck, carried thing from X to Y. There's real time involved, and there's real limits in how fast things would go. And you're excited to think about how best to fit things in time. And time was very much of a thing. All programming languages since, Fortran ignore time as a part of the computational correctness of the program. Time is not part of the language spec in any way, and the program can run faster or slower and be correct, even if slower means millions of times slower or heat death of the universe, still be correct. And I think that's the piece we've been missing for a very long time.
Well, to be fair, C++ did try to do something about it. I think that's the only language which has the algorithmic complexity in the standard. So the algorithm, for example, sort, it's required to be n log n. And I remember implementations had to switch from using quicksort because quicksort could degrade to quadratic. So,
Pull out
of course, that the algorithmic, sorry?
Pull out a spec or something for this, because I do not recall this at all.
From 1998, all of the algorithms have been specified to have strict algorithmic complexity. Every single algorithm in C++, since C++ 98.
When you say every single algorithm, you mean in some sort of standard library?
Yeah, of course.
Yeah, but is it part of the language of C++?
Yes, it's a part of the specification. If you as a, say, GCC or Clang do not supply library, then you are not compliant with the specification. Yes, and there have been changes to the algorithmic implementation of sort algorithms because of that.
Can you pull out this? Because I don't,
Yes.
like I said, I've never had to deal with this. And there are certainly times when I was doing hotspot, I would have cared to. And that sun is still at a bad, and I have to get a better block there.
Wait, sun is not always in the right place for the things you need.
No. It's early morning, or mid-morning, it comes in at a weird diagonal, skipping all shading things, and just lights up my head. As long as it's not light up my monitor, I kind of don't care. But now my camera is like, it's right in my eye. I haven't been in this house for a year, so I don't know how it cycles through the year. My old house, I put a specific shade in for the fall through November, late November. I had to have sun get blocked between 4 and like 7, or it was like right in my eyes. So this is diagonal, high left. It's not my eyes, but it's bad. I need to adjust my block.
Does the JVM ever give you guarantees about when it will and won't deopt? Or it has the right to deopt you at any time?
Certainly there's no time, there's no hard real time, so there's no guarantees. There's, in practice, the high quality implementation says I don't deopt you all the time. So this needs to go into the Google Docs there, Matt, from chat.
I was thinking if you have a limited amount of gas that you want to get your thing done,
yeah,
whether you do or don't get deopted in the middle,
right? So
that deop could cost you,
right,
a gigabyte of processing.
Right. So this is the hard real time guys. This is like high frequency traders are excited to know about this behavior or not. And I want to say not guaranteed, but in practice useful effect was if you ran something realistic, it hit all the edge cases and you quit deopting. And then
this was the run the whole test suite before you connect to the trading system.
Yeah. Run everything once before you connect to this. So you changed your algorithms overnight. You do some big ass test setup just to warm the system up before the trading day starts, and then you attach to the trading system, and you hope that no new corner cases that were not in your tests, show up from the trader, and then throw you into the deopt right when you're trying to do some big transaction with lots and lots of money tied to lots and lots of bits. And everything slows down, and some guy beats you to the punch, and you lose all your shirt. That was their complaint.
This is probably where your easy mode, fast mode could be helpful. You could be like,
exactly.
Once we complete running the whole training data set, we go into the compiler is not going to come on. No memory allocation will happen.
Yeah, right. Yeah, there's a thing that says I want to behave like an embedded system after some startup. I'm going to go through some fixed time. Allocate all my memory, it has to fit, allocate blah, 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 it has to fit. And now I'm all done jitting and I'm going to run without further changes in my performance, except what changes in the inputs happen.
I think this is a step in the right direction. The compiler should support the different modes in the experimentation, and when you're done,
Right.
it should aid you.
So this all sounds fun, and what really happens is that in practice, there are corner cases that are very difficult to handle JITting code for, and if you fall into that corner case and you cannot run the compiler, your options are now limited, right? So like class loading is something you're not going to want to JIT for, and so if a class gets loaded, you just bail out and go rebuild everything. So you could argue that I'll be stable if you quit hitting new code that requires hitting new classes. Like you run this code and you've never seen this class before. Now you go into production and you start running and then you see the class. Well, I claim your test setup sucks. And furthermore, at the point at which it sucks, you know, the system slows down to handle loading the new class. After loading the class, the JITting behavior may change. And what was fast before may not be so fast because you lost all sorts of optimizations that were possible when you didn't have that class loaded that are no longer possible.
But that would require more deterministic when things
Well, or
would happen.
deterministic behavior, like performance of a virtual call when there's only a single subclass loaded is one thing. We inline the fucking call to the max degree and it disappears in this cost model. As soon as you have two or more, you now make a real V call and you lose the opportunities to take loop invariant hoisting of the guts of the different calls out of the loop that was hot, or a bunch of things can happen there. So right away, when you say I added new code to the system, I have to say your performance is now different than it was before, and it could be substantially worse. So the other version of that one is to say you can't load this code, and so now your system has to have a breakout that instead of loading code, upon hitting this funny corner case, does something else like throw a fault and die. You know, you shut down your assembly line. You know, standard assembly line that's got, you know, conveyor belts moving shit and people doing shit. There's a button, or a bunch of them that say shut down the assembly line. Something's out of spec.
Yeah, I think that's what you want is the error handler that says, I'm going to call the scheduler and say, deschedule me.
Yeah,
now I'm going to do a bunch of
something's
expensive
wrong,
stuff
right.
and fix myself up and get to a happy state. And then I'm going to call the scheduler back and say, okay, I can handle traffic again.
Right. So this is the mode that says I handle it at speed of X or better, or else I bail out. Right, that's my hard resource guarantee. I'm done computing your thing in 10 millis or less, so therefore I can handle, you know, 100 a second or whatever the rule is, or else, and there's always has to be an or else, and you have to come up and say, what is the or else choice? And one of them is bail out, stop the thing, and always in these kind of situations, then there's back pressure comes into play. You decide what you're gonna do with back pressure.
So my fear there is that you end up slowing down standard library development because the
yeah.
standard library has to target this sort of most restrictive environment, and everything in the standard library now has to take in and pass me a resource pool because I do no allocations.
I think you can come along and say, this code doesn't have resource management baked in, and if you call it, I give you no guarantees. If you want a resource managed chunk of code to have, because you have a high performance hard real-time guarantee in some place in the universe, you don't call these library routines that have no resource management.
But the thing to consider, Aaron,
right, but
you
how
look
do you
at
design the standard library such that it feels like a cohesive community? Like there's certain places in C++ where people are like, we just don't use the standard library. We only use this library of our own functions for our own use cases. You'll shard the entire community unless you have a standard library that's got a bunch of functions that work in this very restrictive mode.
I think there's a big sea change of attitudes about performance that come with that. And there'll be a bunch of people who say, I don't like time in my language, I'm ignoring it, or it's too hard, I don't care. And there's a bunch of people who say, oh my God, my hard real-time high-frequency trader is whooping ass on everybody else because they take their random pauses and I don't. And I eat their lunch every time they take a pause and I'm all happy. And, you know, same as the missile launch guys or the next Airbus 300X or Boeing Dreamliner, what the fuck, where they got hard real-time, has real life implications that are beneficial. So people who care a lot will care. And they will drive libraries of tools, you know, tooling that says, this tooling is resource managed and that tooling is not. And, you know, as long as the language has a spec, which lets the language help the developer know that when he's using resource managed tooling or not, I think, you know, you have a forward path. Right now, there's a clear dichotomy. I care or I don't. If I care, then I stare hard at all the algorithms I use and all the languages I use and all the code I use and blah, 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 and try and make sure that I get the resource, but there's no help from the language itself. Right. That's the thing that bugs me. There's no language of support here. You know, I switched to real-time Java and I get some OS level support. Real-time Linux with real-time Java. Real-time Java comes along and says shit like, don't garbage collect. Or there's some real finite limits to it or whatever. But, you know, other pieces of that spec are like, and the performance is probably the same once jitting's done, as long as you don't load code. But as soon as you load code, you lost the performance and, you know, fine. I don't know. So we're a long ways from getting there. There are people who care a lot for obvious reasons that it impacts, you know, the real world.
What I was going to say is you should look at the kind of the difference between like what's this micro language that Linux has introduced for
the kernel,
EBPS.
EBPS. Right. So that's the where I really care down to the clock cycle type thing. And I'm willing to trade off all sorts of things to get super high precision and cost management, right? And you know, chances are very, very good that nobody outside of the Linux kernel cares to that level. And that's why I was kind of telling the story earlier about the, you know, like an ad network doing asynchronous transactions, why it makes so much sense, right? Because they don't care if you use an extra 10,000 clock cycles or whatever. Like you know, the cost of managing it is dramatically higher than the cost of the resource.
Yeah.
You know, so depending on how precise you want it, as you back off on the precision, your cost goes to almost zero. So Cliff, think about the safe points you interject in hotspot as you're generating code, right? The cost is zero, basically, statistically zero.
Right.
And that's what you want to do for, I would argue, that's your starting point for resource management as well, right? You back off into where the cost of resource management is zero. Someone steals a couple thousand clock cycles. Oh, who cares? Like, seriously.
And then as you tighten the screws on where you're at, the thing I think you have to do is be able to give people a hard guarantee, even if it's very loose, if that makes sense. And that's the part we're missing here. Like, I guarantee you, out of every second, like, oh, there's this minimum mutator utilization metric that I was really hoping would take off and never did, but it's the right answer. It's at what granularity do I get to have clock cycles to run forward on my process versus clock cycles spent doing garbage collection or other system pauses. And the theory here is that I wrote something that I think will run a straightforward tick, 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 but it depends on background resource management that I don't have control over, like garbage collection, like OS scheduling or inner paneling, like Linux kernel page zeroing ahead of me and shit like that. So it depends on all these things that I don't see, I don't have control over, but I want to know that I make forward progress at a certain granularity. Well, I can say, you know, in the realm of like only looking at young gen GCs, over the course of a minute, I'll lose much less than 1% to the GC cycles and to page zeroing and shit. But if I look at a 10th second granularity, maybe every so often of a 10th second, a young gen kicks in and eats 50% of it or something. If I look at a microsecond, the young gen's more than a microsecond. And so when it kicks in, I lost all of that. So now there's a logarithmic curve you can make here that says beyond 1 second, I get like 99% of my time all the time and I don't care. And below a microsecond, I periodically get zero. And so there are some things that's good for and some that's not. You know, if I'm doing transactions to the exchange, maybe at the microsecond level I care, maybe I don't know. If I'm running a large slow moving plane, maybe at the millisecond level I care, and at the microsecond level I don't. you know, there are frequencies and times at which these things have their threshold, which you care about, but you don't have any way to measure, or it's not a metric that's available. You don't have any way to look at it. You don't have a way to manage it. Say, in this code, I'd be okay with the following, you know, protocol on how much resource management it gets versus how much forward progress it makes or whatever. And that's part of my unhappiness with the lack of support here. There's a real need for this.
I just
And
think
it's
that doing this on a type system would be more complicated than most dependent types. I'm thinking, for example, think about the dynamic array with the geometric growth strategy. That's the most popular implementation of dynamic arrays, when you have amortized guarantees on the insertion or growth of the array. But because they are only amortized, from time to time, you are going to have those latency spikes when you actually have to reallocate the array to, say, double it or whatever. So if you wanted to track this on a type system level, you are essentially doing a dependent type system for the size of the tracking the size of the array, which
you
could be non-trivial.
You could trim it to that. Instead of doubling, you doubled into a cap, and then you added a fixed amount where the cap was big enough that the cost of adding the cap was low enough I didn't care.
Yeah, you could change the implementation, but I'm thinking if you want your language to tell you that you need to do that, then your language is going to be complicated.
Well, that's what I was looking at. Your C++ does something, and I see you have libraries and they have things here, but I don't.
Yeah, and then they do actually only guarantee amortized complexity on the vector insertion. So STT vector is the standard container for dynamic arrays in C++, and they only guarantee amortized complexity for that.
What I'm trying to say here is that how much compiler help is there as opposed to just the users added an annotation?
Oh, that's the standard library for help. It's the standard library that has to be implemented to obey those complexity. No help from the compiler whatsoever if the library offers true help.
So the user comes in and lies. I would say lies, but you know, just is mistaken about his algorithmic complexity. The compiler does not spot it and help you.
Yeah, it's a trusting computing base. I mean, if you screw up standard library, you have screwed up the implementation of the language.
You know, that totally makes sense. Yeah. I think that's a reasonable good first start, because you know, you're not going to teach the compiler about algorithmic complexity beyond the very simple things like I have a loop and therefore it's order in length of loop. But as soon as you want to say I have this doubling hack going on, it's not going to figure that one out.
It's actually super hard because I mean, there has been this talk about standardizing contracts. So contracts proposal is basically Bertrand-Mayer's styles pre and post condition, right? And one of the first issues with the contracts applied to standard library is that it very quickly came up there are assertions you will not be able to check at all. Think about the, again, sorting implementation when the user is allowed to pass an arbitrary comparator, where it turns out the comparator, in order for the sort to terminate at all.
Yes.
Oh yeah, exactly. Very good.
Yeah.
The dependent
The
type
comparator has to obey strict weak ordering, and you actually cannot provably check that the arbitrary user-defined comparator for sorting algorithm is implementing strict weak ordering. So right out the gate, you have a difficulty checking the contracts just on standard algorithms.
The dependence.
Yeah, a bunch of the sorting algorithms behave very weird when you pass in the comparator, always return less than.
Yep.
Yeah.
I recently saw one that used thread locals in the comparator and compared to.
Oh, and was this a multi-threaded sorter? But never mind, that's already treading, bad, dangerous ground. Sure. Oh, geez.
Well, how can you compute a hash code without a thread local? It's okay as long as you record the hash code and never compute it again. So question
Load it from the field.
What's the so where did your query come from? What's the what is the thing that you would like to be able to accomplish or thinking it should be accomplishable? Tell us the big goal.
So it was not a personal goal. It was discussions I was having with people in blockchain crypto groups who were like, we want to have lots of compute, but we don't want every single miner to have to rerun every single transaction forever. This is arbitrarily expensive. So how do you make rules that say we're going to have some computation that is guaranteed and being checked by more than two parties, but we also know that the computation is going to complete in a reasonable amount of time, and you're not just going to get locked up in an infinite loop.
So there's
That's-
proof of work and proof of effort and proof of storage and then proof of climate change.
Yeah, proof of carbon would be tricky.
Proof of
That's-
carbon. Yep.
This is embedded in the protocol. You have to, in order to arrive the state, you have to verify every single transaction. You just can't avoid it.
Yeah. And the thing I've been seeing is Rust code with counters in it that's being compiled to WASM and then run on other people's systems. And the counters end up being more expensive than the useful work often, which led to my question of like, no, we managed to get pause points and save points to be pretty cheap. There's got to be ways to make these counters way cheaper than the sort of first pass at that we've attempted.
First thing I did with non-blocking hash map was discover that the counters were the cost and not the hash map. So I did a striped counter, which eventually made it into the JDK. There's long striped counters or whatever. That's a cheap parallel computing counter. Like atomic, no dropping of any counts, but every single up to the limit of your shared memory machine can increment as fast as they can. And then, of course, HTOE had to have the same thing across the cluster. These weren't going back to your database, to Cameron's earlier question with the ad system, but they went to a semi-permanent storage in memory that was periodically, usually written out by somebody somewhere, but you just gathered counts for however long and wrote them out then. In our case, it was usually on a bumping progress bar for when your algorithm was going to complete. But, you know, 100 nodes running 10 cores each, 1,000 cores somewhere were all bumping the progress bar as fast as they could. And you had to do some reasonable amount of gather and collision handling.
The other problem they run into is how do you account for the cost of syscalls? Because there's the traditional, I'm going to the operating system. I've often written code that is running slowly, and then I go to profile it, and it's like, well, what is it doing? Oh, it spends 99% of its time waiting. Okay, yeah. How do I make this thing faster if it's not actually doing any work?
Yeah. Oh,
The other challenge is the more efficient your code, the more you're measuring the profiler than the profile.
And the profile, yeah, that's true too. Yeah, Kirk has this.
Yeah, a lot of these things are JavaScript or WASM code that is like relying on the underlying browser's web crypto API to do SHA-256. You're like, well, where's my time? All of my time is in this, I'll use the term syscall into the VM that says, please do this SHA-256 for me.
Yeah.
And now I'm trying to meter how much gas you're using, except you're not actually using any energy because all you're doing is asking the runtime to do a lot of work. And then as soon as it comes back to you, you ask it to do more work.
Calls on the runtime that have a cost need to be, they all have a cost. They need to go right to your gas. Absolutely. You cannot call a runtime and say no gas now. No. That's exactly the DOS, the denial of service you're trying to avoid. Hey, I want to go get a temp file. I'm going to scribble some bits and read them back. Oh, I want 1,000,000 temps a second. I want 1,000,000,000 temps a second. I want more temps a second than the heat death of the universe, right? It's a denial of service attack straight up. You just can't let people do that. I want a SHA. It doesn't cost me anything. Okay, I want 1,000,000 SHAs. Hey, your machine ground to a halt. That's totally denial of service attack.
Right, but how do I assign a price to that?
I
can wait for it to come back and then say, well, how much time has passed while the syscall was happening?
Every individual OS call needs to have, that you're going to allow the guy to call, needs to have a cost associated with it. And you need to decide how, some of these things you just shouldn't let them call. Hey, I'm going to do network resolution arbitrarily far removed. You can come back and say, you can't make that call. I'm not going to let you arbitrarily poke the interwebs and wait for a return answer. As soon as you have a thing that says I go off the box and I wait and then it comes back, I claim that you're adding a whole lot of resource consumption somewhere else that needs to be attributed to this dude. So for the easy first answer, say no.
So you just set the prices and be like, oh, you want to do a DNS request? Well, this is how much a DNS request costs. Do you still want to do a DNS request?
Yeah, right. Yeah, right. Exactly. That's the thing. So the guy says, I'm waiting for somebody to update a website X to some new value, and then I'm going to claim that the smart contract has evolved. Well, okay, so the website goes out of business, never pays its bills, disappears, gets put in with a hacker who just captures packets and stalls a DNS attack. It never happens. Every time you make a call to the DNS, there's never a return, but you're not billing this guy, so his DNS attacks just simply accumulate over time. And that's another DNS, that's another denial of service attack.
And there's no non-blocking DNS in Java, by the way.
Just saying.
So
Well,
every DNS request in Java requires a new thread. if you want to do it non-blocking.
Totally go to a cost. Well, you put a timer on it, and then if you have to use it with Java without adding a foreign call, then I would put a timer that shot that thread down. Hey,
I don't think it's interruptible.
Sorry?
I don't think it's interruptible.
Oh, I bet you I can hit it a thread.def and you're down in flames you go.
Will that work if it's stuck in native?
I think Cliff is saying he could rewrite the VM to do that.
No, I'm trying to think. We did a lot of cool shit with thread.def was pretty aggressive, but it might be waiting to come out of native. So you could be correct. You burn a resource indefinitely. So I would claim that you'd have to have a new native call made that had a timer, for instance, and then you just gave it up. I mean, what's he really doing? Somewhere under the hood, he's calling some Linuxy thing that says, please, sir, look up whatever. And the Linuxy thing ran off and went to wherever it goes to the universe and comes back. Just turn around and say, or else after 10 millis or whatever my limit is, come back with a failed.
I traced through it a month or two ago, the DNS implementation in Java. So
the Java one, yeah.
Yeah.
Sure. And it
Did the Linuxy one support a timeout?
So the OS supports all sorts of concurrent non-blocking stuff, but Java doesn't. Yeah, the Java libraries don't.
Yeah, so you might have to add one for that one. Yeah, that's what I'm saying. There's like a sea change that has to happen when you start really thinking about resource management here. Another one of my favorite, whipping boys. I grab my phone and I'm typing something, and something pops up like a notification saying, "Hey, you got a text message," and my finger's already in motion. So it hits the wrong thing. And what really happened was there was a window where my eye to my finger had to coordinate and say, now is time to go, where between that window, somebody changed the meaning of where my finger landed.
I'm honestly surprised Apple hasn't fixed that. It would be such an Apple thing to say, like, no, you probably didn't mean that. Try again.
Right. There's an easy fix. It says, like, the space goes dead for a while. It's miscolored by the OS to be some other neutral color, and it's a dead finger press. And then you miss and you look, and oops, and then then the text message overwrites your keyboard window or whatever the fuck's going on and mess with it. It happens to me, once a week, twice a week. There's some quickie thing. The usual one actually is the damn Swift keystroker thing. I start typing and I see the word that's the default one change. As I'm headed for hitting the default one, it changes out from under me and I get a different default. Okay, it's fucked up. Now I have all those keystrokes I slowly, painfully typed. All of them are lost because there's no backup to where the screen was prior to hitting the, oh, you said, coffee compiler club, and you meant to say whatever.
They have actually improved that. So if you hit the back arrow once, it'll show you what the previous suggested word was.
I want what I had typed to be also put back because I usually have some careful spelling or hyphenation capitalization thing, and he just like wiped it out. I wrote something. He decided
I hear you. I'm with you on that one.
Yeah. Still, whatever I updated, it's still doing it. Shit, fine. For a long time, my metric of choice was try to get your phone to write super autocomplete man with the S and the A and the M capitalized, but all run together. And see how often he tries desperately to make you type something else because he's just so confused. And after about, a month of doing this back and forth with my wife as part of a joke, eventually he learned super autocomplete man. And then he would only pop up super autocomplete man as soon as I hit, SUP, super autocomplete man. No, I'm at supermarket. Stop that. Fine. But that's a timing thing. It's a hard real-time behavior for a UI. So, yes.
So Aaron, my advice to you is avoid hard real time.
Yes. Or at least charge the hell out of it. There's certainly good money to be made because no one else wants to deal, because you have to deal with the whole fucking stack top to bottom.
Yeah, every time we start thinking pause times and you're like, okay, this is gonna be about my code. And then suddenly you're staring at weird operating system configs and you're just like, oh, pause time always ends up in the operating system. Grr.
Yeah. Azul will sell you, a box that does really good on the pause times, but they really reconfigure the Linux kernel. There's nothing to do with garbage collection. It does, but they beat that one down for a long time ago. And now, after that, you go to the OS. I took a bunch of interrupts on this particular CPU, so he's not like we're trapped for performance. Oh, I had to 0 bajillion pages. I didn't have any way to break out of zeroing a 2 megabyte page, so you got to wait 10 millis while I finish the zeroing. And a bunch of things like that all had to get sorted out before you could get, reasonable pause times on one core or some set of cores, and the other cores are doing maintenance and background work, and that's okay. But
So any guesses what you would want for an API for these kinds of restrictions?
not right now. Linux, or not Linux, C, Matt just threw out one from C. So here's an example, and always the answer is, surely I can do better than this. I've been looking at these things. They're like horrendous. And I don't know that they get you any compiler support. There is basically documentation that says, here's the things, like this page I'm looking at says complexity, approximately, and then code, last minus first times log of middle minus first comparisons, and twice as many projections. Okay. That's clearly not a description that is machine friendly. Approximately starts out with, does that mean big O notation of or not? And twice as many as opposed to 2 times, it just rolls into the big O, plus there's a constant factor that I should sort on. Here's another one, complexity. Let n be last minus first. If extra memory is available, in log n comparisons. How much extra memory is not part of the description. Otherwise, at most, n times log squared n comparisons. In either case, twice as many comparisons as whatever, as projections as comparisons.
The extra memory is relatively, well, easy and hard, but the point is that the call to something like malloc, but that returns a status which can fail, either is successful or not. So it's a yes or no answer. It's a check at runtime. There is actually an
malloc was allowed
allocation.
to fail and give you the null pointer. Is that not true?
Well, remember that in general on Linux, you can have memory allocation never fail, even when you're running out of memory, and then your process can get killed if it turns out the system was out of memory. So the point is you may have to write a special allocation function just for that.
So that was a good point here. Like malloc can fail, Java can throw out of memory. Linux says we changed the API, so malloc succeeds always, but your process gets killed.
Right.
There's always a resource management here. As OS must do resource management on you.
And it's arguably most, I remember reading that most software actually doesn't test for that. So people very rarely write unit tests,
Yes.
which exercise the behavior of the software under lack of memory.
H2O had to do that. We did that because somebody fool would come along and say, here's a terabyte of data set. Oh, and I've given you, 10 gigs of RAM, and my laptop can't eat the terabyte, but I'll try it. So we had all kinds of unit tests that said, and what the hell happens when you run out of memory?
Yeah, it's a good test to even try replacing the malloc with the malloc that always fail and just run the test suite for your application.
Well, what we decided was there were lots of small allocations that wouldn't fail in practice and we weren't concerned about, but when somebody loaded a data set, it was always a giant allocation. So we intercepted the out of memory interrupt which gave you a callback from the garbage collector at some point, and freed up a pre-pinned chunk of memory that was quite a number of megabytes, killed the attempt to load or compute. You know, you're making temporaries just part of the calculations. You kill the temp you're trying to make, and you force the GC cycle to clean up all the freed up giant megabyte chunks that came out of that. And then you unravel the rest of the calculation, put it back at the upper level user and say, I ran out of memory trying to compute this. So all the in-between things where you cleaned up and threw out, allocated, of course, and they did things, but they allocated small shit, which was covered by you freed up a large pinned memory to get you out of that hole. Then you re-grabbed your big pinned memory once you cleaned up and told the user to try again. So it kind of sort of worked in like 95% of the cases. You didn't actually crash. You could clean up from an out of memory. But it's only because we had this bimodal memory distribution. You had either very large memory allocations or lots of tiny ones that typically never had very short lifetimes. You just do GC cycle and they'd come right back. So it's a hard problem I've solved for a very narrow case, or partially solved for a narrow case. I would love to see a more general solution here.
Yeah, I posted a link on the way we do it for our containers. And the idea is pretty much you approve something up front, and then when you've detected that it's exceeded it, you basically call a callback and you say, hey, that amount you gave us was exceeded. And then the container is, for all practical purposes, frozen at that point. And you have a choice of what to do. And if you want to give it more compute, you just call the same thing back and give it a new callback. So
you're living with
you get
containers as a unit of resource management. A container can run out of a resource. It can freeze at that run out time, and then some owning container manages it.
right, because the one thing you can't do, as C++ has proven, is you can't return a null pointer on an allocation.
No one's going to bother to check.
So you either kill it,
yeah,
or you say, okay, you can have that memory. There is no other reasonable choice. And
yeah,
that's what this allows you to do. So you say limit memory 1 gig. And if that gig disappears, call me back on this function. And that's the line 399, right? So it calls you back and it says, hey, you ran out of the gig. What do you want to do now? It's like, okay, give them another 10 megabytes, right? And after that, I'm going to kill it, right? Like
right.
there's some.
What I heard you say was there is always an out of memory situation. Of course, there has to be. There's always an out of memory handling because there has to be. Doing it at the malloc level typically leaves you too finely grained, interleaved inside the guts of whatever the user's doing. You need a coarser granularity where you declare success or fail. Same as my safe points. I don't stop you between safe points.
Right.
I stop you
right.
at a safe point. Yeah.
Exactly.
So this is a place where exceptions are actually useful.
Yeah. Yeah.
Or a condition.
Actually, it's not an exception. It's actually an interrupt. It's like an interrupt.
You've halted the one container, and the other container at the API call gets a return from the first halted container that says this container's run out of memory.
Right. So the outer container gets the callback that says, hey, that inner container, you told me to tell you when you ran out of memory, CPU time, whatever. Yeah. I'm telling you that we ran out. What do you want to do? It's your call. You can do whatever you want.
Right. But it's not like you unwound the stack. So it's not
right. The stack is frozen.
Yeah.
Right where it was when it ran out of memory. Everything's frozen.
Yeah.
It just sounds like a very harsh API to be like, you asked for a raise. I'm always either going to say yes or fire you.
Linux killer. Is that not
no. So Aaron, that is totally not true. Look at it this way. Every time you ask for a raise, you get the raise. And you don't know if you didn't because he shot you. And you were not even aware that you were getting shot. That's the point. Like
you ask
for a raise, you ask for a raise, and you just keep getting raises. So I mean, there's no reason to not risk asking for a raise. Let this be a lesson.
Until you get shot.
But you don't know you're shot, so who cares?
Yeah, okay, fine, fair enough. Here's that Cliff guy again, asking for a raise again. He's too expensive. Kill him. Okay. Bam.
Time to go hunting one more time. One last hunt, puppy.
I think I like Cliff's version of the lecture on how to negotiate with your manager better.
Well, I'm of the theory that at some point this evolves to there's a funny money negotiation strategy between competing parties for the limited CPU resource or limited memory resource. And we haven't gotten to there yet, but that one shows up at some point. Right now, the funny money, if you look at IBM mainframe, the funny money was fought between the VPs of the different departments who said, I want the mainframe for my projects and you don't have time for it for yours. So, we fought at that level. But there was a fight for the limited resource. As soon as there's a fight for a limited resource where different people have different competing opinions, you need to move it. It's going to get moved out of the, out of the machine into some sort of a market, wherever that market is. VPs beating each other up and stabbing each other in the back in order to get time on the limited resource, or that turns into something more sensible, like, well, every time I get an extra, 10 milliseconds on the machine, I'll win another 10 cents out of the market. And somebody else can come along and say, yeah, but bonds are taking a dump. We need to sell right now. So we'll make a lot more money. So I win, get out of here, and I'm going to use the machine and the network card and dump all our bonds, and we'll come back around to the options later or something, whatever.
Yeah, but the big problem, Aaron, is that if you try to let the game of life decide how to manage the game of life from inside the game of life,
yeah,
everything dies.
Yeah,
and that's the problem you got to avoid. And that's frankly the Java out of memory error problem. Like, I'm going to tell you that something went wrong, and by the way, everything's broken now. So try to recover from this. I dare you. Right?
Yeah,
it's just not good.
That was the H2O. We could sometimes recover, but very specialized use case.
But when something is broken, isn't that bad somehow? Can you step back?
Well, that's what Cameron's trying to do, is to step back. Like in the JVM, if you run out of memory, all threads everywhere simultaneously run out of memory. And pretty much everything you do involves an allocation to make forward progress.
Yep. And in Java, everything's global. Like, it doesn't look that way, but in reality, everything is global. There's one memory pool for all practical purposes. There's no contained error.
Right. So for the H2O situation, we faked a second memory pool of very large array objects for our data sets. And when you tried to allocate one of those, if you threw it out of memory, we could find them all and kill some set number of them that related to, then we turned it into an application problem, kill things related to a particular data set. And to do that, we had to get memory back. So the handler for catching the callback from the GC saying we're out of memory couldn't itself allocate. And the first thing it did was it freed a megabyte and then told the GC to try again. And then it went and not let any other thread run. So it halted all threads and said, GC, try again. And then that gave us back generally the meg we can now allocate. Now we can start doing like a remote call to another node in the cluster and tell him, free up these things. Well, that remote call required me to build a UDP packet to send a control signal, and he had to catch it. So I had to allocate, and he had to be able to allocate, and all kind of shit was going on with allocations there. It was non-trivial to recover from the situation.
If you look inside the exception handling code in the JVM, there's actually a chunk of memory that's pre-allocated. And then when the exception tries to print out the exception into a buffer, it mallocs or whatever the buffer. And then if the malloc fails, it's like, haha, guess what I have in my back pocket? I have this buffer, and it reaches in the first time and it's got a buffer. And it reaches in the second time and it's like, oh crap, I don't have anything. I already used my buffer, and it kaboom.
No.
You can follow a rabbit only once.
It aborts that printing and goes on to the next thing of printing. That set of, I took an exception while printing, so I did some resource management and tried to print something smaller and smaller and smaller, not smaller byte-wise, but fewer things. That goes like 20 layers deep. I don't know why, because I had to fucking debug that when I took the goddamn dump from Oracle, where they, I wouldn't say they fucked it up, but they certainly weren't aware of any other processing going on than a Linux system over whatever. And it took me, like, I was doing something else when I hit this particular bug, and it took me another month to unwind their exception printing thing. And eventually I did, and it's useful because in nearly every circumstance, you get a decent printout.
Okay, I'll admit I haven't looked at it in at least 10 years, probably.
Oh, it's
15.
uglier than sin. I set a mode bit to saying, I tried this part, so let me unwind and try, the next simpler thing,
So it has 20 rabbits in its head.
It has what?
It has 20 rabbits in its head.
Yes.
When it's pull
And
out 20.
one out after another. Yes. I do complicated debug printers for debugging all the time, where the toString, which IntelliJ will just print for me, they have to handle all kind of misformed structures, because the whole point in here is that I've fucked up some invariant. And so the guy handles nils in every fields, and this invariant is not that invariant, and everything else under the sun. The only thing he doesn't handle is out of memory in the printer. But everything else, he'll print reasonably smart prints for everything, but that's a lot of work.
So the core of the problem is when you start to managing resources, you cannot stop halfway. You can.
Yeah, right. We've always assumed infinite time and infinite memory for the last, 40, 50 years. And yeah, if you want to manage even a little bit, you have to manage a lot. I like your solution, Cameron, of drawing a bigger circle and saying I'm managing the big circle outside of it, and then I don't have to deal with all the little bits inside. They screw up partway through some partial thing. No, fuck it, wipe.
That's the ecstasy version of that's someone else's problem.
Yeah, well, it's the same as the Linux killer. It's the Linux killer just says, geez, I don't know, you're the biggest guy, bam, die. Whether it's the correct one to kill or not, you don't have any say in that matter. You kill the biggest guy and you move on.
I mean, Erlang certainly had some luck with keeping the Ericsson phone switches operational with tricks like that.
I think but yeah, you got to kill and restart, and that was baked into the execution model. And then you got this higher order of quantum effects. So I'm saying, like Java.
Yeah, supervisor trees were a good idea.
Yes, Java's safe points give the JVM a quantum-like effect. x86 instruction execution with wide issue actually has a quantum-like effect. It will not bother to take an interrupt between certain dispatches, because it's going to dispatch 2 and 4 at a time. And so you do not get interrupts randomly at any instruction. You definitely get them at points between where the dispatch of the wide issue does or does not pop in. So there's this quantum effects, and going to the container levels, just raising the quantum size, the next larger chunk. And I think that's entirely the same thing to do. Don't like your language, but I like your containers.
Well, of course you don't like the language. We use letters and numbers.
Why bother? One row on the keyboard's good enough.
Who needs a space bar in their language?
Oh, no, spaces are fine. I use spaces all the time.
You can't express arbitrary expressions in your language using only symbols. Is it really a language?
Exactly.
Just look at
yes,
JavaScript.
okay, fine.
I appreciate Cliff's point of view. I just don't like it.
You just wait till he wins all the code golf competitions against your language.
No, yeah. No, God.
So I was kind of hoping Cliff would already be done with AA, so we could just emit AA as our bytecode.
Me too. And like I said, I got lost in the land of type theory. I'm having a good time dragging my butt out of the land of type theory, and I keep thinking, I just need this one other thing. And the type theory looks doable now because I've had too much time doing type theory.
Because, looking at AA examples, they're definitely MLIR, right? Like, it's a mid-level intermediate representation, right? It's a bytecode.
I think you mean MLIR.
MLIR.
Yeah, that's what I said.
No, you said II.
Machine language.
My microphone is broken.
Something.
Yeah.
Did I miss something at the beginning? What was interference graph trimming?
Some guy asked me during the week to talk about register allocation. And Derek and I had a conversation about register allocation last week. Then I got a separate email talking about it, and this guy had some, I've never done it before, but how about this? And he pulled up a thing that was, reasonably commonly being done in like 60s and 70s as a cheap ass quickie way to go do it. And, missed 40 years of progress. Okay, 20 years of progress. It's been not so much progress in the last 20. I just gave him some pointers and showed him what was good and what was bad. And then he threatened to come on and ask about register allocation. And I know Derek had talked about it last week, so I thought I threw it out as a lead-in. And then we got into Scala, love-hate, turned into hard real-time. Well, you asked for hard real-time. And, you know, I don't have an agenda, so the conversation goes where it goes. Derek wants to say register allocation, you can.
So one thing you've talked about with register allocation previously was you can register allocate to like 16 registers, and then notice you're on a machine that's got 32 or 64.
Yeah.
And it's much easier to go to larger numbers than it is to go from infinity registers to finite number of registers. And I don't think I really followed that the last time you described.
Okay, so this came about because, of course, 8088 or whatever register allocation on virtual machines doing code generation and running on 8 register machines. And the question was, can we pre-compute something that we can inflate into actual machine code on a wide variety of architectures? And the expensive part of that inflation is doing register allocation. So the cheap bad inflation is everything's a virtual register. You don't have enough. So they're all in memory. So every register operation is actually a stack-based operation, and you die to death with 1,000 stack reads and writes. You really need to register. So can we pre-bake in a register allocation into the emitted code? So we're going to emit some machine-independent neutral format, architecture neutral distribution. What fucking people had these names for these things, ANDEF and all this. And you know, think Java bytecodes, but they were becoming popular, and everyone who wasn't Java bytecodes was like arguing that they had a better distribution format than Java bytecodes, right? So what are the other formats that you would think about? Well, something I'm going to inflate, like WASM. I'm going to inflate it into hardware instructions, but I want certain properties, and I want it to be cheap to inflate. Well, the big cost of inflation is register allocation. Okay, so how do I make that cheaper? Well, I want to run on an 8 register machine, and I want to run on a 16 and a 32. Is there some way I can do them all? And if you boil it down to 8 and you arrange the 8s to be in pairs such that if you actually had 16, instead of going to memory for every other one, you took your pairs and said, these guys can coexist now because I have double register counts. And then again for 32. And so there was this theory that says I could pre-allocate to an 8 register machine and also mark pairs such that if I was actually on a 16 register machine, I would get rid of the loads and stores for the extra things and say, you guys actually live in a register instead on a doubling by doubling basis. Never came to pass. There was an academic paper I read in conference 20 years ago. It was a cool idea. A lot of cool ideas never come to pass. Fine.
Well, the main thing is that if you're producing code at runtime, the problem is boiling it down to the number you have, not expanding it to the number you have.
Right. This is how fast can we execute, and the answer is I can typically expand something like a reasonable bytecode, not Java bytecode, but some more reasonable bytecode into machine instructions faster than I can get them off the disk.
Right.
So all costs are related to, I just keep it in this compressed format. I blow it up in my caches and run it in my caches, even off of main memory versus caches. And it's big memory savings and runs fast. Okay, I have to emit code now. And I can compile ahead of time. So I pay all my compile costs by compiling ahead of time. So that lost the whole benefit of compiling on the spot, but you get the profile data on the fly. And the goal there was just to make, and
I've told you the statistic. I've told you the statistic before, but the Java team, when they were profiling to try to improve startup time, they found that almost all of the startup time was reading from disk. So
yes.
the actual, even if they JITted everything, the JIT ran dramatically faster. Even coming off of flash drives, the JIT was faster than the flash drive.
Yep.
And that was like 7 years ago. So flash drives have gotten faster, but still.
Yeah. This conversation has come around several times at Sun and at Oracle, and I've been part of them a couple times. Yeah, and they've gotten better at it, but they do it by not loading so much shit. It's fine. So back to the JITting thing, you actually wanted to, register allocate for peak performance. You wanted to register allocate on the spot because you got profiling data and not pre-compile. But back in the day, 20 years ago, the concept of JITting was still like, that's too expensive. You can't do that. And I was fighting the compile speed wars for a very long time. And this paper is about compilation speed. It is a faster way to do a graph coloring register allocator. And I could never get it published because I wasn't comparing linear scan to graph coloring. I was speeding up graph coloring. And the people at the time were not excited about that, even as the faster compiler won the day and everyone uses the faster machine. I couldn't get the academic community to admit that it was interesting. So, unpublished paper, a couple published attempts made on it. I claim it's worth a read if you're doing a register allocator and you have a speed issue you want to deal with, compile speed issue you want to deal with. And actually, it makes a decent graph coloring allocator in general, independent of everything else. It's a good start to graph coloring allocator.
Would you use an allocator like that if you're going to be aggressively inlining?
That's the whole point of it. It is specifically, so the aggressive inlining leads to too many live ranges. And that problem is solved a different way. This guy lets you write bigger interference graphs and therefore have more shit, and without the n squared blow up biting you so bad. So it's a faster way to compile. It takes the n squared part of that whole curve and takes the big extra n and knocks it down by a bunch. So it takes a big chunk off the speed. You're still n squared, but with a much lower growth factor. Okay, having said all that, it's also a fine start to an allocator where you have way too many live ranges. But now to solve the problem, you have way too many live ranges needs intelligent spilling, which this paper is not talking about. And that was also part of the hotspot things. It's like, this is speed, and the other one is, where did I have the paper up? Just in my face. The other one is doing more intelligent spilling. And this guy, yeah, this guy doesn't talk about that. It might, I don't know. Maybe that never hit a paper. There's a giant ass comment at the start of the hotspot Chaitin CPP about how the hell we do the spilling. And that's where you get, or win or lose too much inlining is spill management.
So where in the JDK source is that?
That's
Would that be in?
So I go to click, Dropbox, I think it's under programs, not Emacs, JDK, I have JDK 7 source code lying around. So I'm a JDK 7u-hotspot. I have a source, share, VM, opto. Boy, how many times did I get that? And now I'm in the C2 compiler, and you'll see things like click, portions of code donated courtesy click.
Yeah.
Okay, so I go to Chaitin CPP. And I used to have, where's the giant ass?
Here.
Chaitin HPP has it. Of course not. No, well, I still recognize this code though. It's very scary. Been forever. I thought I had a fabulously giant comment. Here's one of them. Register pressure, that's part of the deal. There's the simplify logic, biased coloring, select, fix up, yada yada, derived basis, stretch. There's a lot of big comments in there, but they probably don't make any sense without having enough. Boy, I do not see and clear in my head the memory of a large block comment that described what the fuck we were doing.
Could it be that it aged out and it's only an older version?
Yeah, maybe. But the code's all there. I'll bet you if you look, the count of changes in this code is probably next to nil. Because it was doing a good job and it's really complicated to go deal with.
So the Chaitin is the
Bridge Chaitin allocator. You can find papers on them.
Yeah, but
That's
that
the base.
Chaitin.cpp,
Yeah,
which is 2,500 lines of code, and HPP, which is another 800.
yeah,
That's the allocator?
yeah. Them two files. I want to say at one time it was closer to 5,000 lines, so somebody must have outlined some stuff, which I probably did at some point. It's fine. So, right. So, GraphQL
I see a comment
allocator.
here that's about a half a page. It's got a table about reg pressure. It's on
Yeah.
change.cpp line 900-ish.
Yeah, start at line line 209. Says phase Chaitin : register under allocate. So I'll put this on my. Let's go put this on. I'm gonna hit the share button here. Not the. I have to whack my. Oh God, what? What happened to sharing? Okay. What happened to? Oh, advanced, no. Portion, files, no. What happened to screen sharing applications under Zoom?
When I click it, it says host disabled participant screen.
Yeah. I've disabled it in general because spam bots, blah, blah, blah. Okay.
Yeah.
So I hit it now. You should be able to share. I'm trying to hit the share button. And I don't have Emacs as an application. I don't have IntelliJ. I don't have, like, IntelliJ is a modern app. It's not like a older, what the hell? So you're sharing now.
Yeah.
Oh gosh, and you love black on white. That's nasty.
Well, here I can.
Okay, go find. No, you're way down low.
There you go.
Go find. Let me get rid of full screen here because I got a much bigger monitor than you do. Go find : See, I don't have search built into your thing. : register under allocate. That's the start of the universe here. Yeah, right. Okay. So this is some high level discussion, and then it starts breaking down to interesting things.
Okay.
So the high level discussion says that I have an infinite number of stack slots, and I'm just going to allocate things into registers, including stack slots. And if I run out of registers and I spill, I use the register, which is a stack slot. It's another register. And then I set up areas for doing work. So the arenas for split arena and live arena, a little above your mouse now, are just allocation for storage. Then I call phase live, which computes liveness. And that's the interference graph trimming is happening in phase live. I'm sorry, in IFG, phase IFG will be having it. Phase live will be computing liveness as a bit vectors, double bit vector. The come out of SSA to the named world adds names. It actually leaves SSA in everywhere by having names. Then there's an if def verify. And then there's a phase trace. That's just a cheap ass. What phase am I in? Do some reset. Let's see what's going on here. Interference graph init. Gather live range masks. This is part of the trimming game where you decide what is the intersection of all defs and uses of registers allowed. And do I like run out of registers already because somebody's deft in one register and used in another, and those have fixed named registers, and I'm just out of registers. The obvious one being all calls return a value in like RAX, but take the first argument RCX. So if you pass a return from one guy into a call the next, your live range has no valid registers. You must split the live range to move it from AX to CX.
Where are you looking here?
So gather large masks, go above 10 line, go down. Yeah, right in there.
Oh,
so
yeah,
gather large masks, live range masks says, find what registers are allowed for this live range. Could be none, could be empty. Could have lots, could be empty. Then go compute liveness based on who's intersecting whom and where things start and stop. Stretch base pointer live range is the next chunk down is because I have derived pointers, which I don't know if you do. I have pointers to the middle of objects, middle of arrays. So the allocator keeps the base of the array somewhere, anywhere, and it will spill typically to the stack if it's not being used directly, and mark the register as derived from this other register so the garbage collector can move both of them the same amount. And that computation's done. Stretch decides to do the stretch, and if he changes something in order to stretch it, he moves a base out of the last use out of a loop to span the body of the loop. He has to recompute the live range masks and the live range stuff. And so that's the conditional clause there. Then there's an interference graph that's built once using virtual registers only. So it includes stack slots. It was a triangular list. I squared into a bit vector. That's your n squared. You do coalesce, you need the bit vector version for the coalescing. Coalescing says a bunch of live ranges that are related to each other because of phi functions become the same live range. So I was in SSA form, and therefore a live range looked like a def use edge, and it hit a phi, which is its last use, so it was done. But no, all the phis have to be the same live range. So you coalesce. There are places where I break cycles out of phis, like if you do Fibonacci, you always get bad overlapping things, and you have to split cycles right away. And then you go down to the next phase. This is a more, oh, this is first coloring attempt. Yeah, okay. And the first coloring attempt almost always fails. So I've unrolled the coloring attempt, and that's the aggressive version above with coalescing. And then the coloring attempt typically fails, and we're gonna have to spill. And so I didn't, after I color, you unwind the coloring, and you put things back in, and you decide you lived or died. You build a physical interference graph, no virtual registers now. And you must spill typically, and so I go through and I recompute and break things out and add more bits and pieces or whatever. And there's a split call eventually made down in there. And then there's a, out of memory, there's a bunch of out of memory fail checks going on in there that says I can't allocate you, so I give up. But at this point, I've insert my first round of spilling. Typically, that spilling is done to do everybody who couldn't possibly ever allocate because they were in RAX and RCX required both, and they can't get both. So now they've been split. Fine. Okay, then renumber all my library just down low. So a bunch of them got deleted or got added or whatever. They got renumbered low. So I have a dense n squared graph. I don't have to do any sort of weird, funny biases or have holes in or anything. I renumber the interference graph. Makes it a bitch to debug because all interferences from pre and post the compaction phase got renumbered, and you have to track them across. It's a bitch. Fine. And then I redo things. Now I'm heading into the go retry spill loop. There's go build your interference graph. There's go build a physical, go get your live ranges, go get your interference graph. I'm down to the bottom of the screen now. Go square it up. Go attempt to do a game there with effective degree, which is lets me do some coalescing where I know I won't break the colorability of the graph. So this is one of these mini optimizations that you add in after the fact, after you have a well-working allocator that says, in this case, I don't have to keep it split. I can get rid of junk copies because this doesn't actually increase or decrease the computability of the graph, the colorability of the graph. Carry through, there's an if else on the opto coalesce version, and the else version just says square it up and compute degree, and then go prepare for simplify and select. So there's some setups, so we're getting into the hot loop of the allocator body. So this is all the unrolled pieces yet. Whereas I'm trying to find the starting loop, so keep scrolling down now. Cache large info, here's the while trip count, while spills. One last round. So the first round of spilling was almost always failed because of direct conflicts of registers. Second round of spilling sometimes succeeds straight up, especially for small functions. So you simplify, you select colors. If the color comes back with no spills, you are done. You've got it coloring, and you walked away. Otherwise, now I have a trip count where I bail out and say, I'm for whatever reason, I'm stuck not getting an allocation. Usually there was a bug in the allocator, so there was a bailout for saying, hey, I failed. Here's why I was failing, usually because I'm splitting, coalescing, uncolorable, split the same thing again, coalesce it again incorrectly, and then can't color it again and split it again, and yada yada. So that was carry on. So then in the middle of the screen, I split you again because I came in here after your original spill, so I know I need to split. Here's the set of things to split, so they got split. Recompact after the split.
Am I reading this incorrectly, that you'd have a hard time with more than 16 million variables?
Yeah. There are some hard limits in here. It's clearly, we got bumped past the 65.5K limit a long time ago. So it wouldn't actually run out of 16 million directly. It would instead run on memory in order n squared. But things like 4 Fortran conversions from FPPP, a giant unrolled function, into Java, and then allocated as, tests, would often have 600 things simultaneously live. Like the peak set of live things would start at the start of the function with rapidly ramping up to several hundred live. Then it would gradually climb to 600 things simultaneously live, and then gradually track it back down to several hundred live when you got to the end. Okay, you can't, you have to spill like a mad dog in such a situation. You just have to incredibly spill. He survives. So many tens of thousands, yes, 100,000s get slow, but it totally works. I don't do millions, or I don't expect to test well at millions, but in theory, it should work at millions. So anyhow, you're in the middle of the hot loop. You compact live ranges and you reset everything again. You rebuild your interference graph. You gather your masks, compute your liveness. You build your interference graph. You spill. You compute degree, and you respill at the bottom, and you loop back to the top, and go again, and repeat until you get a coloring or you went 24 rounds. And usually, he's highly normalizing. He usually gets you in like 2 to 4 rounds. Bigger functions will be 4. Small things go in 2, and you're done. Little accessory things all went in that first eager unrolled pass that did some other stuff. And even small functions often go in the first guy. If you had to spill something at all, you often still went in the second guy. That was still quite common. The big loop here was for bigger functions, and he, like I said, he's strongly normalizing. You generally got out in 3 or 4 rounds total. So once or twice to the big loop. So you can see it's a huge ass thing. I have a bunch of things in here to do with memory management. I have a bunch of things to chop down the constant factor in the big O. I have a bunch of things in here to do profiling. I have a bunch of options that I turn on and off according to as I added various kinds of better allocation, but that weren't necessary. There's a lot of debugging help baked in, but if you throw all that out, it's still a complicated algorithm.
Yeah, definitely.
So what you didn't see in here was what we didn't get to is like select colors and spilling, wherever the spill thing went. It was above you now. Now you're in the cleanup code. And the cleanup code says you do obvious things. It's building stack frames and doing math for how big things are. And since you graph colored your stack frames, they're actually typically really small. There's things where if you roll past things where I've converted x86 ops, memory ops, happened in, see now people you're down below you now. So you're back to the big loop here, it's fine.
All right.
You don't have to worry about it. X86 has many instructions, convert sys spills at the bottom of the screen.
Yeah.
So many instructions can be just updated in place without actually inserting any code. And then there's let's see, move important info out. Yeah, so the live range data was used to select things. Now I went through a large, complicated, I pulled shit out and I started getting ready to pack it into debug info for the garbage collector to sort on things. So there's now a game where I'm going to the machine description files for what registers are. So right now registers are all like a bit and a bit vector that I pulled out very early on. You didn't see it. Now I'm going back to the bit vectors and I'm mapping bit number 13 maps to register RES or RESI or whatever the hell it maps to, which goes to this pattern in the instructions when I actually go fix up the fucking instructions. Or I can't actually do it as a memory-based mode. I have to go add an actual spill or whatever that's going on in there. There's some shit in the middle here for the vector registers as well. That's a third register set for x86. Yeah, that makes sense. Fine. I don't know. I would skip this as a lot of, I went from my bits, which were the fastest way to do graph calling allocator, to something that looks like machine register bits.
Yeah.
And then there's some memory management and cleanup and you're done. So it's a big ass thing. And then there's a lot of support functions all over the map. And, look at some of them or other than like the spill guy tries very hard to split, it's the split guy, very hard to split live ranges in a useful but not high cost way. So an easy example is I have a loop which has some hot shit and I'm out of registers. I want to split around the loop boundaries. so that I can put things in the loop, and then I'll pay a spill cost outside the loop. So as a generalized version, I have block execution frequencies, and I want to split at low cost blocks that transition to high cost blocks.
So are you actually keeping loop depth information here, or it's just you've got it down to like execution counts per instruction?
I convert loop depth to execution counts. So sometimes I don't have any frequency profiling data, and I just go as loop depth turned into execution frequency on a power of 10 basis. Sometimes I have real counts. Sometimes I have a little of both because I got some inlining here and some not inlining there, and some profile here and not there and whatever. And there's a giant blending stage that happened before I got here, turned it all into execution frequencies. They are often powers of 10 related execution frequencies. There's a minimum cap you get to, and you powers of 10, you only get 30, or you run out of bits in your exponent for your double precision guy, right? In whatever, you get 23 and you run out. So if somebody writes stupid code, you can run out of bits and you can't go to 0. So there's a bunch of games played, but execution frequency now. Okay, so then still the splitter says, I'm in a low frequency, it's cheap to spill. I have a slide range spanning a high frequency. I want it to spill so that it goes to the stack. So I have registers available in the high frequency. So there's a bunch of games played where I say, I'm going to spill this guy or not. And one of the goals is to say I have 2 hot loops, and different things are in use in each hot loop, but they're different, and they're going to span the other hot loop. You must spill around the loops to get, useful registers in the middle of the hot loop. There's a bunch of things like frequency goes to all the deopt code has known execution frequency of extremely cheap. So it tends to gather spill code, like it just gets piled in on the deopt side because no one cares. You're not going to take that code anyhow. Then you have to push it to the end of the function. And that's block layout, which happens later. And then you don't actually care to like do coalescing or tidy up the registers in the very, very low frequency blocks because it's execution time, it's compilation speed versus the code will never execute anyhow. So like statistically speaking, we'll never execute. So I don't care what performance has in it. So there's a bunch of cutouts that say, hey, you're too low, I'm not even gonna bother here. I'll have to color you, but I'm not gonna make any effort after that. So the splitter has a lot of fun games he plays.
Do you ever throw stuff straight onto the stack without just saying this stuff is low execution, I don't even want to bother looking at registers, just throw it on the stack, or you just give it a low?
No, you go through the normal path, which will very rapidly, the splitter splits live ranges, he doesn't put them on the stack, he breaks them apart. As part of breaking them apart, he allows the broken live range to have any register, including the infinite stack registers.
So is that split really just you're just sort of inserting a move in that?
Yeah. Literally, I insert a move. I declare it a split move, so I know that it's an inserted split. Its goal was to, prevent conflicts of registers. And either end is typically the load and the store in or allowed all registers, including stack or any other register. Then when you go back to coloring, if I don't get you a nice, fun, x86 register, you'll definitely get a stack register.
Right. So you just make the move target interfere with the move source, and then you're kind of good, and it'll definitely. Yeah.
So right. So yeah, the every instruction knows whether the live range for its input value overlaps with its output or not.
Yeah.
So like if I do an increment instruction, the live range of the value coming in ends at the instruction and a new live range starts coming out, and they can use the same register because they don't overlap. Whereas, and you might have another use for the increment afterwards that prevents that, but the increment itself will not cause you to have an issue there. That's not true of all registers. All instructions, the value of the register is used throughout and is not, it might die at the end of the instruction, but you can't have it be the output register. And that's, like I said, that's on an instruction by instruction basis. And RISC chips don't have this issue, but x86 definitely does.
Yeah. Okay, well, I'll have some fun. I'll read over this code. That's a good intro. I'll probably have to come and watch the video a couple times.
Yeah, and a lot of this is just like education on how bad it can get, and education on what are the big important parts. If you do your own, and I wouldn't suggest starting from this, do your own, you know, you're going to start with something much, much simpler.
Yeah, well, I already have a simple graph coloring register allocator, and it does an okay job, but it doesn't do any live range splitting, and it doesn't look at any information about loop depths or frequencies or anything.
So go straight to frequencies fed from depths. If you don't have profiling, just feed it from depths, but go straight to frequencies so you can add in frequency choices later that are not related to depth. Like I said, the deop path here where I give up, I don't give up very often, because if I did, you would suck. So give ups are rare. Therefore, the deop paths are all extremely low frequency. Therefore, you want to teach that to the splitter, because they'll do something different there.
Yeah.
In particular, you can split in that block for free and immediately free up the register for whatever follows outside that block.
Yeah. Okay, and I have to find the last time we talked about this as well. So because you kind of went through the algo at a bit higher level. So yeah, I'll see if I can dig that up.
Okay.
Yeah, well, thanks.
Yeah. And I see you're using Emacs, the correct editor.
That's right. Well, it's a good editor for doing closure stuff for sure.
For closure,
almost caught up to VI.
Yeah.
Well, especially in evil mode. So, which is what I definitely use.
So look on the right-hand side here. This is this is like frequency games going on here. So a little further down from your mouse, it says opto-debug split frequency. If a basic blocks is 0.1% execution for the method as a whole, then I declare it a debug block, and I will be much more happy to eagerly split in there to free up things. And also I will aggressively drop things to stack during the coloring. Like you won't be allowed to go hurt somebody else's allocation at all. High frequency blocks take more than 1/4 of the total execution time in the block. That goes to the spiller where he says I have a high or a low frequency block, and if you're spanning a high or low frequency, I'm going to spill eagerly. Like this, the most eager splitting is you split at every depth and every use. There's always too much, almost always too much. So the first rounds of splitting always start around frequencies of things. If I start doing the main loop and going 3rd and 4th iterations, the next time I split that live range, it splits at every depth and every use in an effort to get a coloring just to get the fuck done. But the first go around is split around the loops, or high frequency, low frequency, whatever those are.
Yeah.
And then live range structure is coming up, and maybe we shouldn't go there. It keeps going on and on, but whatever. And I have a guy who's just sent me at the start an email, and Yaroslav, it's brand new, and this is hi. And I don't have you. Okay, let's kill a screen share for a second. I want to say hi and get the 10-second intro from you, guy. Can you say something?
Hello.
Yeah, there you go. Yeah, 10 seconds. Like, what are you doing with compilers in life? You gave me an interesting tweet.
In the last time or at all?
Why are you here? You mentioned the word Kotlin and JVM backend when you talked to me. So why are you here?
Because of my general interest in this area. So it's interesting for me even other runtimes and virtual systems, or virtual machines.
Okay. Okay.
Welcome.
So I'm just curious. I think that's the best time.
Yeah, welcome. And you're just right at the end, and so we might do some cleanup and then we're done. And next week you can you'll get the invite next week as well. So
Okay.
actually let me just do quick here. So do you have any questions you want to ask people here?
No.
That's fine. Okay. Well, Does anyone else have anything they want to say or ask here? Like we're in the middle of giant register allocation things.
Well, something that I had been actually reading in the last couple of days is about type lattices, and I actually
The last year and a half.
Oh yeah, and so I have it. I mean, it seems like a really good approach. It seems like I can make sense. So I have a fairly complex system in the set of different types of things that I need to be able to on the hardware level that I need to be able to deal with. I have another screen share I could do. It's a little chart.
Yeah, well, I could screen share right back at you at a lattice that I have even up right now in a in a graphing doc to sort up my types.
Yeah. So this is one, and I've been trying to figure out if this sort of drawing it out yesterday.
Yeah. I have these charts all over the place.
Yeah.
Yeah.
So basically I've got a risk machine, and it's got basically integer types. So I was thinking signed, and then lower than, or like more specific is unsigned.
Yeah.
And then, my false and true are here.
Right.
And I think that stuff I understand, and I was looking at your AA source, and it seems very similar, like it's kind of inspired by that.
Yeah.
So, but then where I'm a bit uncertain is if it makes sense. So I've got like kind of two machines glued together in my system. It's a risk core and a 512 PE array. And each PE has a small number of registers. They're byte registers, but sometimes they're sort of grouped in D words. I'm fairly certain that this yellow part I should delete, and I should only think about bytes, because this looks like a disaster.
Yeah. So I've been doing this game for like I said, a year and a half now, and I've started with, or I've come to, like, there's some properties I want out of my lattice, and I have strong reasons for wanting them. You may have different reasons, and you may want different properties, but the properties I pick dictate what my lattice looks like. And one of the properties I'm interested in is a symmetry across the center line, because it means that I can evaluate operations. It turns me into a church roster one-step property. I can evaluate things in any order, computing types, and I'll always get to the same answer. Furthermore, it's not just the same. It's not just the same answer per se. It's you always get a single best answer, or most general solution. You get the same solution. And if you got this on an SSA form program in the first place, you're guaranteed linear time. So the lattice wants to be bounded and symmetric, and be a lattice, it has to be commutative and associative. And given those properties, you get a hard guarantee of a fast answer to a fixed best answer. Okay, so that dictates certain actions that you may or may not want to put into your lattice. So demanding symmetry means that any byte by byte needs to have a match down below.
Yeah.
So byte by byte goes to some sort of collection, or you're going to get rid of it in any case.
Well, that's what I'm not sure, because I don't know if this is even possible, or if it needs to be then like a totally separate lattice that you're like at least need to split out into a separate thing or something.
Well, okay. So the next thing that you notice is that you get these splits and joins in the lattice, and where you fail have matching splits and joins, like the lattice branches out like a ever increasing, I don't know, whatever, and then it rolls back together.
Yeah.
If you've failed to get it symmetric, there'll be a path where you'll get an answer that's not the best. And then that will turn into, you get weird runtime bugs, or you get weird compile time bugs where you failed to find something reasonable, and you fiddled something nonsensical, unrelated, and now you did. So you need it symmetric in that way.
Yeah.
There's a bunch of other things. So the next thing I think is useful here is I found that the lattice properties, when I got complicated, were difficult to verify manually by inspection. So I wrote a bunch of tools to help me verify my lattice. And in the AA source case, there's source code, there's a section called test lattice. It has a bunch of lattices, which are very simple. They're lines of text describing the nodes and
I was looking at that, yeah.
After a node. And the test code following it verifies the lattice is commutative and symmetric, and a lattice has a meet and a join. It's easy to say it has a meet and a join. You obviously look, but as soon as I can pull up the Wikipedia page and show you trivial lattices that look like they ought to have be a lattice and they're not, because they fail to have a join or a meet, because there's two paths to from a guy to two different guys that are both, you know, least common. That means you're not a lattice. That immediately means your fast algorithm can fail, either by running forever.
Yeah. So it would be good to test. I think I got that property.
Well, so yeah, you have a good picture here.
Crossing lines.
Yeah, there are some things you've done that I was screwing around with a little differently. So like you have null and any struct and comment null pointer, or struct is a struct pointer. And you have no structure inside your structs.
Yeah, it would be, I guess, a struct pointer. And one of the things about the structs in my system is that they're all created in advance by the compiler. I can't create one in the language.
Oh, I see. Okay, interesting.
So that just simplifies the language.
Yeah, right.
And I have some.
The body of a struct doesn't have a set of fields that are user specified.
That's right. Yeah, it's just created by the. So like I have FIFOs, and they have, you know, they have a little circular buffer.
You have a finite count of structs.
Yeah.
Yeah. Okay. Fine. Okay. See, that simplifies life a lot easier. I have generic types for fields inside structs, which means this graph repeats itself recursively.
Oh yeah.
Which in turn means you have to be, there's some other properties you need to make that happen actually. Yeah, sure. So I guess my big easy takeaway here is as soon as you get a little more complicated, you want to have a way to test that your lattice is actually a lattice.
Yeah.
The next thing I do is I have a meet and a join. However that's done, I use a dual and a meet, which is, for a symmetric lattice is equivalent to a meet and a join. And then I have a bunch of tests where I build a bunch of elements in the lattice, like canonical instances of every int of, you know, I don't need all 1, 2, 3 up to infinity, but I need 1 and 2 and negative 1 and any and unsigned and signed and top and true and false bottom and reachable and unreachable. That's a U and R, so reachable and unreachable. It's all fine. And I throw them all into a big pile of types, and I do an order n squared, actually it's n cubed at some point, test of this sample against everything else and verify that I'm associative and commutative and symmetric.
Yeah.
And that immediately found all kinds of places where I needed to fix weird corner cases. And then they became less weird, more common. And then when I got them all sorted out, you know, all kind of bugs that had been biting my butt 2 years ago went away. So nowadays, when I go hack my type system, say I need to add a new thing. So it's overloads. Overloads are choice things. I pick choice of your kind of your set of things up top. And error cases are where I have multiples underneath at the low end where I say I'm both a struct and a 17, and that's not sensible, so it's an error.
Yeah.
I had to go back through and verify that all these properties hold, and they typically do not. And I spend, you know, a week getting them to hold again, and then suddenly all the bugs go away, and shit flows like you expected. It runs through.
Yeah.
So it was very useful to have a direct test on the lattice that was not written into the code because it was too difficult to change and make quickie fixes, and then direct tests of the one I'd written in the code to verify properties for a set of useful, for canonical example sets, which I probably have, you know, 100 or so examples now because the structs got complicated, and the function pointers, I have function pointers in my lattice, they get complicated, shit like that's going on.
Yeah.
Otherwise, my lattice, this looks very similar to my lattice.
Okay.
I threw unsigned and reachable, unsigned, reachable and unreachable into top and bottom, just so I have one top and one bottom. Yeah, I stretch the U all the way up to the top and the R all the way to the bottom and hide it in the middle there.
Right.
Put the card in, whatever you're gonna do,
So
right?
yeah, I was just going to ask whether that could actually live in the main lattice, or if it.
It does. And then my meet operator starts by doing a triangulation of all the choices. And then it does a virtual call to the left, which typically does a virtual call on the right. And the same guys end up in the same piece of code, and they quickly get smart about their internal structures. Like the ints have a type int specific logic that says I'm signed and then unsigned, and this is how I meet and join and yada yada. Whereas the triangulation has a top level simple version, which immediately says, oh, you're mixing structs and ints. They have nothing in common. Go immediately to, risk unknown value.
Yeah. And then, I had this as for, if I'm in the case of a condition, I just sort of want to get rid of all the detail.
Yeah,
but is that?
I would throw that top and bottom out and put false and true directly to your top and bottom and have them. So for me, I put false and true in with the ints, but if you don't want them in the ints, totally reasonable choice. Just
I have them here.
I'm sorry?
I have them here as.
I'm saying don't have a separate lattice. You get to one lattice because it makes your life a lot simpler in dealing with properties that are useful. They're trivially, these two guys, the false and true, are trivially members of this whole lattice. Just merge the one top for the false true to the main top. Same for bottom.
Yes.
And immediately, just like your U and your R, they're just part of the main lattice sort of trivially. And you could throw them into the ints, but then you have to deal with unsigned and signed as well. I claim that that's not the property you're expecting out of your int lattice.
No.
Because false is actually 0, and you've written it as 0, but if you want a Boolean value, it goes to any risk. Yeah, it goes to any risk, not the top and bottom, it goes to any risk. Yes. There you go. For me, I made false and true just be ints, and it doesn't matter. It's all good. What's the tool you're using
anyway? But you treat them separately, kind of.
Yeah, I mean, Java has the annoying property that I have to convert from zeros and ones to trues and falses. Kind of often happens, and I'm always annoyed.
Would you do one of these, or it's not?
In your case, I would claim you probably don't need this. So another thing that comes out of this is that you can add and subtract precision, exactly what you're attempting here. Add an any bool, all bool, but any risk value that is in a context where only bools are allowed typically does the job, and you don't need an any risk or not.
I see.
I have top for me because right underneath top is my X scalar and scalar, which is the same as your any risk and all risk. I don't use unknown, I use all, any and all, shorter words, fine. And I have unsigned and unreachable and reachable, fine. And I have memory contents, which I'm exactly tracking, but they're not any scalar value. And I have, there's another one that's not any scalar value. I don't care, fine. There's a couple not any scalar value things that are, and I just put them in the same lattice because it makes life easier. I don't have separate lattices. Now, as soon as I go to the scalar side of things, trues and falses in your world, I would claim fit the any all scalar paradigm just fine.
Right. So you'd actually do any scalar.
I call it scalar instead of any risk value. Yeah, that's just my name for it. And same point in your lattice.
That kind of goes right there.
No. It's any scalar because your struct is actually a pointer to a struct. Because you can't have a null. Null and struct don't make sense together. It's a pointer to a struct. So your little red area is perfectly fine. I would say struct star pointer, whatever, and any struct pointer and all struct pointers.
Right, I see.
Okay, now having said that, that's a scalar. Having said that, I don't need any scalar as a separate from any risk value. I would declare any risk value to be a scalar, but any risk value is fine. Your case, you're distinguishing between things that are on the risk chip versus things that are on your programming element devices.
Yeah, that's
important. Which is totally reasonable. It's not that is nothing to do with my lattice, has no whatever's here, but that's a totally reasonable thing to do.
Yeah, because that's one of the challenges is that I need to do things like register allocation in this thing totally separate from in this.
Yeah, so register allocation is not part of the lattice. The lattice in my head is what is the meaning of the elements that are being carried here?
Yeah, I guess what I need from this is to tell me which system I have to do the register allocation of a variable in.
Okay, I claim that the lattice is not going to tell you that. I think instead it will tell you shit like this is an uninitialized PE, or this sufficient PE has some interesting value. It's an any, which is an uninitialized. Maybe I don't need to register allocate on it.
Yeah.
Or it's an all, I don't know. Or maybe there's constant versions where I can replace a PE with a shadow structure, which is all constants because some guy's got a 0 that they've shoved on a PE because they want to have a handy 0.
Yeah. So I can't think about individual PEs. I have to think of I say PE here, but it's really all the PEs whenever I'm talking about this. I can't distinguish them.
So that's a replicated, that lattice is replicated 512 times.
But I can't make any distinction between them at all.
Yeah.
So,
At any distinction. You have to know your register allocator will tell you got 2 different guys.
Yeah, so I have to register allocate for them all as if they're just one.
Okay.
And so I think about one PE, but that thing that I'm doing in one PE is happening in all of them, and I can't do different things in different PEs.
Okay, so it's a SIMD calculation.
It's
model.
a SIMD system, yeah.
Yeah, fine. Which means that the types, it's really question is what are the types that you put in the PEs and what do you care about those types? What would you like the compiler to know? If they're just a wad of bits, then I think you're done already.
Yeah, I want to know that I want to know that it's like a distinct value. Like if I imagine, I don't know what the values are, but I know they're hash codes kind of thing. That's kind of what I get from like which word line a value comes from. So it's like it's created by it's, you know, it may be a weight matrix for address. And so I know which byte out of the weight matrix I've loaded up into the SIMD, right? And so all of the SIMDs have their corresponding byte from the same sort of place in the weight matrix. And so I need to, but I want to know that so that if I ask for it again, I can, you know, value number it in the sort of the same way.
Okay, that's not going to do, the lattice here isn't helping you. It's telling you the kind of values that are rediscovered at a particular point. In the case of like true and false, you can constant fold code away. In the case of 1 plus 2, you can add them away. And in the case of a null pointer or not, you can again use if test to constant fold away kind of things.
Yeah.
But it won't let you know how the register allocation is going to land, or the fact that you pulled out of a weight matrix. Are you going to then optimize the generated code some way because the actual flow values, because it came out of a weight matrix versus something else? Like I know this is a weight value, therefore it's between -1 and +1 or something stupid.
Yeah.
By the greater than 2 test on the PE side is dead.
Yeah, so there's also where I think it helps me is there's also some config that I have to do on the PEs, and I do it by loading memory values and writing them into the PEs.
Mm-hmm.
So for instance, I may want to, I may have, say, 5 separate patterns for different configs of way I'm going to set up the PEs. Mm-hmm. And so I want to say, okay, I'm put them all into config 1, and then I'm going to do some stuff, and then I call a function, and I don't know what that function did, but I want to guarantee that when I come back, I'm in config 1. And so I want the function to be able to tell me it's changed this.
Right.
It's changed the PE array, it's changed the config. Right. The config is now config 2.
So put the configs in a register.
Yeah.
And register allocate them. And the calling convention will tell you whether you must restore the config or you're allowed to trash it, and the caller has to deal with the trash config or not. And that's a register allocation problem.
So move it into here and just register allocate.
No, nothing to do with the lattice. Move it into make a new register. The lattice is the values that show up in the program's IR at a node. Also, at the same node, you have some registers. Eventually, you'll be picking.
Yeah.
But the lattice is not telling you how to do register allocation. So what I heard you say was, I have some state, I want to manage state across calls. That's register allocation.
Yeah. Right. Yeah, and I have registers here that I need to do allocation on, so I need to,
Right.
I need to basically know when a programmer declares a variable, if it's going to go to this side of the tree or that side, and then
Yeah.
I'm going to use, they'd get register allocated in here or in here, and that's
Right.
one thing.
So it makes sense to have a type for the PE's variables in your IR that says this is a PE typed variable.
Yeah,
But distinctions of a PE variable internally are perhaps not useful because you're not going to read the distinct type during code transformations and decide that I am going to kill some code because it's live or dead or whatever. It's not flowing useful data through the PE side. It's just a marker to say, and here's a PE thing, and forevermore I'll treat the contents of it as a black box, and the PE will do what it does with it.
right. So in a way, I could probably consolidate all of this into one node.
Right. Without knowing your problem any better, I'm guessing that you can consolidate all those. You have a useful marker that says this is a PE computation, and I don't do add propagation of constant adds on PEs.
Yeah.
Right.
Yeah.
So like I don't expect to do 1 + 2, and usually it's address array math where you scale and add 8 as an offset to whatever, and 2 times 8 is 16. So you added 16. Yeah, addressing math happens all the time. You're not going to see that.
Yeah.
So they're all black boxes. They have nothing useful. You can't tell them apart across the PEs anyhow, because somebody may load up a 1 and somebody loads a weight matrix of some other value, whatever. They're all different. So I claim with my feeble understanding of your problem, you could crunch those down into it's just a PE thing, and I don't know.
It certainly makes it an easier place to start.
And later, if you discover that it's terribly exciting to understand that in some parts of the graph, the PE node type is actually knowable as a 0 or not a 0, and I'm going to do something about it, you can add it back in.
Yeah. Yeah.
The other
Right.
thing to do is you claim it's one of the any risk scalars. It's just a pile of bits. So it's an I32 or it's an I512 or whatever as the PE version, but it fits as kind of like a bland integer. And it's typically always the any or the unknown, the any or the all flavor of your int. Your pile of undistinguished bits.
Yeah. Okay.
Yeah. Okay.
Great. Well, I'm glad
Yeah.
we.
So now it's my turn to share for 10 seconds, and I'll walk away because it's I can't fucking share. What happened? I can't even share Open Office. Why? What happened to? I can't change the size of the share window, whiteboard, or screen. I can do my entire screen.
When
I
that
will
happens
share-
to me, it usually goes away after a reboot. I don't know what causes it.
You've seen this before then. The unable to share an individual app. Like here's the whole screen share. It's like a giant thing. Now I have this thing in the middle, which probably looks a little bitty. And all I'm pointing out here is I have twiddle int is your all integers, and my twiddle scalar here is your all risk values, or any risk value in any integer. And this is all integers. Choice of 0. I have a weird thing going on here. Choice of here's any integers way down at the bottom, and any risk value, or all risk values. I'm sorry, all risk at the bottom. These include nil. That's the and nil comment off to the side here. So temp question mark means it's a type memory pointer. It's a pointer to memory, or a nil. So it could be a nil pointer. And here's some sample pointers to memory strings, and here's some sample integers, and so on and so forth. Then I get a complicated lattice, and I have another version in the lower left corner where I say it forms a cube to help spray it out differently. And this is complicated because I have this funny game I'm doing with nil that you're not doing with nil, so you don't get this complication. You don't have one of my orange boxes, and then you get rid of the whole yes, nil, not nil. But I have like in scalar, here's in scalar, in scalar. So any risk value that is not nil, including not nil pointers and not nil integers. And that's a thing I can do that maybe doesn't make sense for you. So just pointing out.
What does it mean to be a 2 and a 0?
The and is 0 means I have to support the 0 coming through. So some of these combinations are not sensible to deal with, other than they fill a hole in the lattice to give me the symmetry property. It won't change code generation, for instance. But it will
So
change.
it's something that could be a 2 or could be a 0, not something that is simultaneously a 2 and a 0.
Yeah, 2 or 0 is the top box where it's an or. And then when I say or, in this very special meaning, it's the choice the compiler chooses. After you do an if I'm not null, then you're a 2 and not null. And the choice has gone away. The compiler, so that's the other way around. Damn it, I don't have a good example right now. This is I don't know yet what you're going to be, and eventually you'll get bound to either 2 or 0. And it's part of the complications that come about because I bring nil out to pointers and ints and floats and function pointers equivalently
Okay.
for all of them.
So is
If
it
I
fair
do-
for me to think of 2 or 0 as to be compiler's choice between 2 and 0,
Yeah, you
and
don't
2
get that
and 0
by-
to be universe's choice between 2 and 0? So you better be supporting both.
So the compiler's choice means you have an uninitialized variable, which you don't get to write that in the language. Same as in Java, you can't write an uninitialized variable. So instead, as part of the type analysis, I'll start you at the top box, the twiddle scalar at the very top. At some point, you may fall through the, I might be a 2, or I might be a 0, I'm not sure yet, and eventually you'll fall down. Oh, you're definitely a 0, or you're definitely a 2. So it shows up as the in-between state during type analysis, during constant propagation, but it's not a state you can write and manipulate as a user. I have the C code that shows the example of what you can get out of a compiler with an uninitialized variable, and sometimes it helps people understand. Here, I'll go to the Google Docs, which I can't share either. It's like, what the hell, what happened here? So it's this kind of code. So while, say, true, or while some predicate, and I'm going to have, let's see, what is it? If x equals 0, then I'm going to call statement 1, and we'll assign x to 0. And we'll say int x, and then else, I'm going to say statement 2, and x equals a 1. Okay. So in this guy here, in this code I wrote, x is uninitialized. If the compiler chooses a value, and the semantics are clear that he's allowed to choose, he can choose a 0, in which case this loop runs statement 1 only until you hit your predicate fail. Or he sets x to non-0, and you can only run statement 2 until the predicate fails. So here's the point where the compiler can choose to have a loop that loops on statement 1 or statement 2, and both of those semantics are correct. There's another semantic which says I loaded some stack slot at random from a C's X variable on the stack. I got a random value that was pseudo randomly picked by the OS launch of your process. And then I either ran S1 infinitely or S2 infinitely, but it might vary from run to run to run, which one I get infinitely. So that's a case of an uninitialized variable being used in the code, and it screws with these lattice optimizer and constant propagators. And the very simplest ones, if you're naive about it, you can shoot yourself. If you're very simple, don't do anything smart, you just lose, and you emit code for both S1 and S2, and the runtime pick for you when you launched. If you're smarter, you can complain I'm an error because you're using an uninitialized variable in the test, and it never gets initialized anywhere except after the test. So that should be an error. There's another version which says my optimizing my global constant propagation algorithm didn't crash, didn't fail, didn't do something stupid, but he picked one of 0 or 1 and carried on, because the naive implementation of a constant propagator says start everybody at top, load the values and see that they are consistent with, and if they're not, update the type and put your neighbors on the work list and repeat. Here, X is a top, it starts at the top, you test if top, because it's top, you don't know which branch goes, you assume neither goes, because neither goes, X remains top, you're done, you had a stable solution with X top and neither arm executed. That's the obvious way to run standard global constant propagation, sparse, but not sparse, conditional constant propagation. it's not necessarily the answer you want. So if you come along and complain, I'm using an uninitialized variable, you'll get an error here. If instead you're like Java and you say, well, you got an initialization of 0 at least, you don't have a problem. But you start everything at top, and then you would say, oh, X gets initialized to 0. And then you hit the loop and you say, oh, if 0, and then it's 0, and you're done. And you got the answer and you're done. So to make the algorithm not terminate eagerly, is that the right answer? I want to have no initialized variables in the program. But to handle the cases where I know partial information, but not total information, I have to handle the case of I might be this or that until later I discover I'm one or the other. And so you get these partial situations of 2 or 0, and then later it comes out. I can write you the 2 or 0 version of code as well. It's pretty much the same. I just mix a 2 and a 0 and an if, but I don't know it's going to happen yet. And until the if settles out what its answer is going to be, I don't know whether I get a 2 or 0. So it might be a 2, and it might be a 0, and it might be both, and it's not going to be neither. So you end up with a 2 or 0, and you carry on. And that's part of the incremental algorithm. You can't fix an order that said I always tested before I got things necessarily. Yeah, life's
So
not complicated.
Do you don't, so if you get something, set something to 2, and then maybe it'll set it to 0, then you keep track of its 2 or 0. You don't just go straight to its
If it's
all,
2 and 0, I go straight to you're an int.
all int.
So get the difference between 2 or 0 or 2 and int. Yeah, in the land of hotspot, I do ranges. 2 and 0 goes to the range 0 to 2 with a widening count of once, because after so many widens, you just go to infinity or you'll endlessly widen. In any for
Yeah.
loop with an x plus plus, the range thing has to terminate or you widen indefinitely. Okay. 2 or 0 is a funnier case.
Well, 2 or 0 could be true or false if it comes through an if statement. If it's 1 or 2, I could imagine it being more useful because you come to an, you already know enough to say this is basically always true.
Right. So I did something nasty. I ended up with x is 2 or 0. I don't know which one it is. I don't want to, for whatever reason, I haven't evaluated the question marks to a reasonable answer yet. But I can say definitely x is 2 or 0, which is definitely less than 3, which means immediately I can say that the else clause is dead. And that might help me discover that the question mark has a particular answer, which immediately helps me get a better thing later.
Right. So you do sort of have sets in this system. Sets of values.
Well, the lattice notion supports sort of arbitrary precision, and you decide by your definition of the lattice how much precision you find useful.
Yeah.
I find it useful to distinguish nil from everybody else. But in the land of hotspots, small integers, distinction was a minor performance gain because you got things like enums with switch statements and you could tell whether it's partial coverage and do shit like that. But they didn't typically help very much. Size matters for ints sometimes, so I'm keeping track of the size. I have a int 8 versus an int 16 and an int 256, but not really a range anymore. But I could add a range in. As long as it fits in the lattice, I can add it after the fact, and then the precision just gets sharper.
Yeah.
It's
Yeah.
also
So it
saying
seems like
once
the best strategy is to start as simply as you can.
fairly coarse lattice. Yeah. Know that you will need more engineering to support a more complicated lattice to make sure that it's actually lattice. So start simple and get everything else going. And when you're ready to upgrade, be prepared to upgrade your tooling too. Like you'll probably upgrade your lattice once or twice, and then you'll upgrade your tooling to make sure the lattice, because you'll hit these weird bugs, and eventually you'll diagnose as I broke my lattice, and then okay, I need tooling for the lattice, and then you add tooling for the lattice.
Right. And tooling, you just really mean test suite.
Yeah. Yeah, intelligent test suite. So the tooling is some of it. The test lattice in AA is an entirely separate lattice description. It's a tool that lets you describe lattices sort of more directly, and then verifies all the useful properties that you want out of it.
Yeah.
And in fact, if it fails to verify, it gives you an intelligent error message about how your lattice could be modified to make it match the properties of choice.
Yeah.
The testing for the testing guide is just testing. I have a thing in there called check types or check symmetric or check commutative or something stupid like that, and it runs every time, and it does the big. Is my meet symmetric or commutative? I swap the arguments and verify they're the same, and then I do distributive laws and associative laws and all kind of stuff.
Yeah.
But those came about as hard lessons from my lattice got complicated, and then the bugs got complicated, and then you get into places where you're doing the meet, and you play whack-a-mole where I fix the meet here and it breaks over there. So I run over here and fix the meet and it broke over here. So I fixed this one, and you've got a bunch of tests going on, things are bouncing around, and you eventually kind of stabilize, and eventually you realize you have two places you can touch one or the other, and you're always broken left or right, and then you boil it down to two tests. And then I get down to one test where I can do this fail or that fail. And then you realize your lattice was broken all along, but it took you, half a week to go diagnose your broken lattice.
Okay.
Fine. It's the whack-a-mole that took forever. I fixed it. Yay. This
So
test
broken
worked.
lattices are a disaster. That's what you're saying.
Yeah. Broken lattices are a disaster. Yeah. The simple ones are easy to spot. Complicated ones, and they got more and more complicated. So yeah, test on the lattice itself. All right, fine. We're well past time. I need to go pee.
All right. Well, it was fun.
Yeah, very entertaining. I don't get to talk lattices very much. I'm very excited to do that. All right. Until
Okay.
next week. Bye-bye.
Bye.
Bye.